So hello everyone and welcome to this next lecture in the DC-DC converter series, and we will continue with simulating the transformer. So where we had left off in the previous lecture was we had simulated a high frequency transformer, that is a 5000 Hertz transformer, but we had kept all the simulation parameters the same, which means we had kept the integration time step the same, the control sampling time step the same, so everything was the same except that now we were simulating a high frequency transformer. And we saw that as a result, the simulation results were wrong. We see here that the primary current and the secondary current are actually out of phase, which is quite obviously wrong because there is no need for these two currents to be out of phase. So this shows that simulating a high frequency transformer would need a change in the simulation parameters. And that is what we will do in this video. So coming back to the simulation, before I start, as always, a bit of brief background that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length videos in the MOOC website or courses on the MOOC website Udemy. And this is one of them, simulating power electronic circuits, that is simulating power electronic circuits using Python. And in this, I talk about the basics of installing Python power electronics, some basic electrical engineering and power electronics, and finally ends with a case study of how to simulate a buck converter with closed loop PI control. And the second course which I have is more on the signal processing side and is titled Basics of Digital Signal Processing for Power Engineers. And in this I talk about the basics of signal processing, how to use Python tools to generate frequency response characteristics, and finally there is a case study of how to design a low pass filter and a notch filter using frequency characteristics and with Python packages like NumPy and SciPy. The last course, the latest course rather, is simulation of magnetics for power electronics using Python, and in this I talk about the basics of magnetism, how we can use basic concepts to simulate an inductor, a coupled inductor, and also a transformer. And there is a case study of how to simulate a flyback converter. So if you're interested in these kind of online courses, the links for these courses is provided in the description for this video, so please do check it out. So getting back to the lecture. So as I said before, in order to be able to fix this problem of wrong simulation results, or rather the currents being wrong, the first step that we will do is we will change the simulation parameters, right? So let's go back to the main page, edit circuit parameters, and you see that the integration time step and the time step of data storage is 1 microsecond. Now going to the control file, we will find that, well, actually it's more on the circuit parameters. Let me go back to the circuit parameters. So the voltage source here, as you can see, is 10,000 Hertz. All right. So we have a high frequency voltage source. This is just an intermediate step before we actually start simulating DC to DC converters like flyback and so on and so forth. But this is just to tell you about the effect of high frequency. So since we have a frequency that is now almost, you could say, 200 times what it was before, you would say that in order to be able to simulate this new system, which is 200 times faster, your integration time step would be necessarily 200 times smaller, right? So therefore, what I would do is I would decrease this integration time step by an equivalent amount. So let's say, for example, if you were to divide this by 200, right, what that would mean is we would get, simple mathematics, let's go over to this. And if I were to do 1.0 e raised to minus 6 divided by 200, I get 5 e raised to minus 9. So what I would do is I would change my integration time step to this value, that is 5 nanoseconds. Right? So let's go over. You are of course welcome to play around with different values, and I would suggest that that's always a good exercise. So I have changed my integration time step and my time step of data storage. Now the time step of data storage does not have to follow the integration time step. That's very important to understand. This is how fast I am storing data so that I can plot it. So this can remain 1 microsecond, right? Because the question here is how much detail do you want in your plot? Now, unless you are worried that your data file is too large, it is a good idea to maintain these the same, because then you can track transients in your simulation much better, right? So with this, we are done. We can go to the output page, but before I run, it's important that we also change the control file. Now in our control file, this has a time step, right? This has a time step which is 1 microsecond. This is the sampling time step of the control file. This is how often this control file is run. Now this will have to match the integration time step because we are solving the transformer magnetic equations at this sampling time, and we would like this to be as accurate as our integration time step. So we shall save this and let us run the simulation. As always, go to the command line, make sure there is no error. There is none, so we are okay. So now we are simulating our system at a much higher speed. Now what that means is this simulation is going to take much longer. But first, let me just plot the transformer current just to make sure that at least we have a stable system, right? Now you see there is some amount of instability, but the only way we can actually know if this settles down to a stable value is to wait. So this simulation will take time, and there's no way out of this. The smaller is your integration time step, the longer your simulation will take, and that is one of the reasons why I said that decreasing the integration time step should be your last option. Do not jump to decrease your integration time step whenever you see this first step of instability. So I'm going to pause this video and I'm going to come back when this simulation is done. All right, so see you soon. So hello and welcome back, and the simulation has been running for a while, so let us now plot the results again and see how far we've got. So I'll go over to the web browser and click on the transformer currents again. So one of the problems with simulating at a lower integration time step is you just have to wait. There is no other way out. And even with very complex simulation with several converters and large systems, simulation just takes. That is not much you can do. You're solving a system. The bigger your system, the longer it takes. So the only advantage of using something as in this case, as opposed to many other simulation softwares which actually use the system memory, or rather the RAM, is that those kind of softwares, rather commercial, many other softwares that I've used, tend to hang the system after a while. Whereas when you tend to write, or rather when you tend to use a system where you're writing data into a file and plotting it, the chances of hanging are much lesser. So anyway, let's check out the simulation results. We seem to have got something. So the simulation is indeed working. Of course, as you can see, it is hard to see because this is a high frequency simulation and therefore the waveforms have high frequency. So what I will do is I will zoom in. Let's try to zoom in at this last cycle. Let me choose a time period between 0.009 and 0.01. That seems good enough. So I'll go back. And I will choose 0.009 and I will choose 0.01. So let me plot it again. Surprisingly, when your simulation is large and you collect a lot of data, the major challenge is actually in plotting, because plotting data requires you to deal with a large amount of data, and it also results in a lot of data being loaded onto your memory or RAM, right? So now of course most systems do have a decent amount of RAM, therefore like a 4 GB RAM is almost normal. But given the fact that our simulations, we are also stretching the limits of our simulation, we could also run out of that in the future. So there are several challenges. Well, it appears like I've actually closed my file browser, so let me open it again. I'm not sure if it crashed or I closed it. So I go into documents, the energy series, simulations, basic transformer. So this is where so this is the plot. And as you can see, this is more or less what we were expecting. This is what we got even in the previous case. So here, as you can see, the primary current is smaller, the secondary current is larger. The reason, we have a step down transformer. So therefore the primary winding is the high voltage winding, so it has a lower current. The secondary winding is the low voltage winding, so it has a higher current. And we have also seen that this secondary current is not exactly double the primary current, because the primary current is drawing the magnetizing current from the source, right? So we have exactly the same result. So the conclusion is, the only reason for that incorrect result was the wrong integration time step. So this is the importance of choosing a integration time step, right? So with this, there is one last thing we need to talk about, and that is the transformer parameters and why it matters. So let me just stop this simulation. And let me go back to the simulation parameters, and let me tell you about how simulation parameters do affect the stability of the system. So let me go back to our usual 1 microsecond integration time step, because now we dealt with an incorrect result. But what I would like to now talk about is the unstable result. So here, let me go and also replace So you see the system is much slower, and that is one of the reasons is because we've been running a long simulation. So I am changing this back to 1 microsecond. So now that I've done this, let's go down here and let's look at our parameters. So you see the F rated here is 50, because until now I was actually simulating a 50 Hertz transformer which is being supplied with the 10,000 Hertz voltage source, right? Now, that's not acceptable. A high frequency transformer has a totally different design and has a very different set of parameters than a low frequency line frequency Hertz transformer, that is 50 Hertz transformer. So to begin with, how does it affect? If we look, this is where we are doing all our calculations. Let's assume that these are the same, right? So let's assume we have the same voltage ratio, the same VA rating. The only difference comes in how we are calculating our parameters. So for example, we are calculating our inductances, and we are using, in this inductance calculation, we are using the frequency, the rated frequency. When you choose a low frequency transformer, you will quite obviously result in much larger values of our parameters. That is, the inductance will be much larger, the leakage inductance will be much larger, and so will be the magnetizing inductance. Now, what happens if I choose this to be the same as the line frequency? So for example, I have a 10,000 Hertz source which I am now supplying to a 10,000 Hertz transformer. Now what happens? The result is these inductances are going to be much smaller. That is the self-inductance, the leakage inductance, and the magnetizing inductance, as well as this mutual inductance. Now the question is, how does it affect? So let's go and run the simulation and see what happens. Let me just go back once, make sure I saved the file. Yes, I did. And let me go to the command line, make sure it's working. Yes, it is. There is no error. So we are good to go. Now let me come and plot the transformer currents. And let's see what's happening. We get nothing. Okay, let me do it again. Maybe there's a bug, because we should have gotten something at least. Yes, so this at least shows there was maybe a slight bug in matplotlib. Let me go to the command line and see if there's an error. Usually there might have been error, but there might have been some bug. It's always possible. But now you see this is the result that I was looking at. This shows that our values are 10 raised to 304. Really speaking, this is an unstable result, right? And why is it unstable? We are simulating a 10,000 Hertz transformer at 1 microsecond. Alright, the parameters of the transformer are totally different than they were for a 50 Hz transformer. So this is when integration time step becomes critical. Before, integration time step resulted in an error in the simulation. Now integration time step results in instability. A wrong integration time step results in an unstable simulation. So in this, I will stop this video now because it's already gotten pretty long. In the next video, I will talk about why this instability results and how we're going to solve it. Right? So as before, if you have any doubts, please do post in the comments or send me an email or message me on social media, whichever is your preference. Otherwise, I will see you next week where we will continue with the simulation. So thank you so much for watching and goodbye for now.